Okay, good afternoon. Thank you. My name is Dennis Grove. I'm the program manager for the Renewable Materials Thrust. I am the other Grove, in case you're tired of seeing us today. But I'm going to give you here we go. Let's try this one. Kevin Edgar is our thrust leader. He's not able to be here today, so I'm going to go ahead and try to get through this. Trying to get through his section of this presentation as best I can. The Renewable Materials Thrust right now consists primarily of the Bio-Based Materials Center. They have faculty who are focused on polysaccharide cellulose and on proteins. There's also folks in the center who are looking at biomass conversion, degradation of biomass into biofuels and other biomaterials. We have folks today, Ryan Singer and Binu Zhao, are going to present 2 seed projects on increasing biomass. So we sort of have both sides of that equation. And there are 2 projects that ICTAS has funded in the past that I want to cover as well. They're pretty significant. As Matt mentioned, increasing transparency, talking to you all about how ICTAS makes its investments is important to us. You can see here that funding for this thrust totals about $280,000 this fiscal year. You can see how it's broken up. I will point out that most of the money there for the thrust budget was used to purchase an instrument, and I'll talk a little bit about the instruments that have been purchased not just this year but in previous years with thrust funding. The standard ICTAS investment in a sponsored center is $75,000. The BBMC is one of those centers, and the seed project funding is for the 2 projects that you'll hear about later. I don't have a dollar amount on space, but as anyone who's got a lab in Randolph Hall could attest, spaces in brand new functional labs is pretty valuable. So we do have 2 labs downstairs in this building that are used by 3 research groups in this thrust. Okay. One of the projects that ICTAS has funded in the past, our funding ran out, but it's been picked up and is now funded by NSF to a substantial degree. The PI is Jake Soka, and you can see they have a really nice interdisciplinary group of faculty there, and they're looking at how nature manages the flow at a very, very small scale, and they want to take that knowledge and apply it to man-made systems. And so you can see in the picture, I thought it was a really great picture. It's a thorax of you can see a tracheal system and the thorax of a beetle, right? But you can see on the scale it's 200 micrometers. So nature can move liquids through very, very small spaces and do it very efficiently and very well. And so that's what they're studying. We have also funded in the past another substantial project in sustainable agriculture. And this one's led by Joe Gabbard and Jerzy Novak. And what they did is they took this irrigation system that you install underground, and it allows very precise delivery of water, fertilizer, and even gases directly to the roots of the plant. As you can imagine, you can save water. You don't overdose with fertilizer and have runoff. And I didn't know this before, but the gases also impact the growth of the plants. So you can actually feed through oxygen or nitrogen or some combination of gases that impact the plants. They laid out a field like this, and they put sensors all around, and the sensors are monitoring the soil conditions. And in the next stage of their project, they're working with collaborator Al Wicks to develop a robot that will have visualization capabilities, an electronic nose, and further be able to monitor the health and condition of plants. And you can imagine that all this data coming from these sensors all throughout the field go into the computer, and you can use data analytics to then inform the farmer to make better decisions about how to grow crops in the best way. So it's a pretty neat system. It had a really neat impact, so I wanted to highlight this. there is a group of refugees from Somalia that have been relocated to Roanoke, and these folks were farmers back in Somalia, and these folks used this system and these fields that Jerzy and Joe set up to grow plants and flowers, and vegetables, and then they sold them to help generate a little bit of income for them. And this was really neat. They got a lot of local press in both the TV and newspaper, and President Steger highlighted this in his end-of-year video. So really nice project, and that is continuing. Even ICTAS got it started, and that project is continuing on. I mentioned before, thrust funding this year and in past years has been used to buy a number of instruments. I'm going to point out just a couple of them, but we're really, I wanted to point these out because we're really showing how this funding increases research capacity at Virginia Tech. There's a twin screw extruder in Mary Roman's lab downstairs. It's very interesting. It's very useful because you can use it to process very expensive compounds. So as you can see listed, and the reason there is because the sample size that you need is very small. Just one of the projects, sorry, I should mention, all of these instruments are being used by a variety of groups and a fair number of groups, and they all are producing publications and presentations and even IP. So I can't highlight all of them. I just wanted to bring up a few of them. But you can see here in the picture up in the left-hand corner some of the output from this instrument, and Marin's group is using this to make filaments that fabricate bone scaffolds. So sort of what she's doing with those. Judy Riffle has an SEC in her lab, and I think the really neat thing about this one is the triple detector, where you can measure the viscosity. You can measure viscosity, light scattering, and refractive index, and use those to characterize polymers. And like I said, she supplied me with a number of different projects and outputs, and I thought was great. But I wanted to point out this one because you can definitely see in the diagram in the top the three outputs from the triple detector, right? Each color is one of the detectors. And this is an interdisciplinary project with Judy Riffle, who's in chemistry, and Rick Davis, who's a chemical engineer. I thought that was nice. There's an ion chromatograph in Scott Renneker's lab, and again, I'm not going to read all the text to you, but they are looking. He is using this. That instrument is being used to look at the composition of polysaccharides. So he's looking at evaluating feedstocks and the conversion of biomass into different biomaterials of interest. And one of the nice outputs from this is a collaborative project with Scott and Justin Barone, and actually has led to a provisional patent on their fractionating process. So these instruments have been purchased in the past with ICTAS funds, and they're being used to increase the research capacity here. Okay, this is Kevin's section, so I'm going to muddle through as best I can. The Bio-Based Materials Center is an ICTAS-supported center. Kevin presented this information in much more depth several weeks ago at the center review. And what he presented is that going forward, the Bio-Based Materials Center wants to take their expertise in polysaccharides and in proteins and sort of look at that area of overlap, look at the protein-polysaccharide interactions that control the processes of life. Okay, so going forward, that's a big push. Some little more detail in future directions are listed here again. These are fairly specific research goals and will be pushed by the center. Some of the activities and highlights that I wanted to emphasize here are first off, this educational grant from USDA, very substantial grant used to sponsor students to go through the program been very successful. The BBMC was also successful in getting a graduate certification, in a graduate school certification in bio-based materials, and they're actually going to have students graduating with that certificate hopefully this year, so they expect them to finish up. And every year they have an annual student-led graduate research symposium. This past year, the keynote speech, so what happens is all day the students come and present, they have posters and the students present their research in the symposium format, and they have a keynote speaker from outside. And this year they had a person come from the FDA to talk about their work. So that's another really nice program BBC and BBMC puts on. I wanted to show some of the totals that I think are just very impressive, and this is since inception, so it's over the past 3 or 4 years. They have pulled in external funding in excess of $6 million. This is center faculty. They have more than 130 conference presentations and invited talks. They have almost 100 publications and a high number of intellectual property. So, unless there are questions, I'm going to start with our seed project reviews. I believe Ingyu is first. He's going to talk about his project increasing the biomass in switchgrass.
Thank you. Good afternoon. Thank you, ICTAS, for support our project. My lab is actually working on switchgrass. We try to elucidate the regular role of microRNA in switchgrass biomass production. So the team, including myself and also HRB, and also in Department of Horticulture, and we have one PhD student, 2 research associate, and 2 technicians working on this related project. So while we're working on switchgrass, as we all know, biofuel, to make the biofuel be really be profitable, you need to provide cheap, high amount biomass feedstock. And switchgrass already produce a lot of biomass. They can be grown in marginal land, which won't compete with our current food supply. So that's why USDA and DOE all chose switchgrass as a major or most promising biomass feedstock for biofuel production. So we want to understand why certain plants can produce more biomass than the other plants. In the future, we can use genetic engineer method, making other different culture or different plant species produce more biomass. So our major hypothesis is some microRNA regulate the gene expression, and those genes mainly involved maybe in photosynthesis, making plants to be more efficient on photosynthesis, because they can harvest more solar energy and produce more biomass. So I just show the picture here. That's the one plant material we are using. So as I already mentioned, why we study switchgrass, in plant breeding field, the most efficient way to produce super or new plant cultivar is using a method called hybrid breeding. So you use 2 material, 2 germplasm, which is very different. You cross them to each other. So it essentially mix the genetic material from 2 different plant line or germplasm, and then you combine all the good genes, and then the plant will kind of become a super cultivar. So this method has been widely used for plant breeding. So like corn. So 40 years ago, corn yield is very low actually. In the last 40 years, just because plant breeder widely using hybrid breeding method, they increased triple time of corn yield actually. So right now, we also want to apply the same breeding method in switchgrass to see whether we can use hybrid breeding to breeding super cultivar of switchgrass that can be used for biofuel production. So we also, of course, want to understand the mechanism why they can control the hybrid breeding or hybrid vigor. So in switchgrass, they have essentially 2 kind of ecotype, and they are very different. And one called low-light ecotype, another one called up-light ecotype. The low-light ecotype, meaning collected from the south part of the country, they like a warm temperature and they use a lot of water. They produce relatively more biomass. And the upland switch grass, meaning growing in north part of the country, and they like the dry land, the more efficient on water use efficiency, but they produce less biomass. And you can imagine if you combine the good tree or good property of the lowland and upland together, you make a hybrid between lowland and upland switch grass. You're going to have all the good trees come from different switch grass germ plant, and then this plant can be producing more biomass. However, this two lines cannot be naturally crossed to each other. So the main reason is most lowland ecotype, they have 36 chromosomes. So chromosome basically that's the genetic material, or the material that carry the gene actually. And the upland switch grass, they have 72 chromosomes. So they do not match to each other. So you cross these two lines together, this one has 36 chromosomes and this one has 72. They are not matched each other, and the plant can be died or not produce a viable plant at all. So that's let us make hypothesis. Can we making the lowland ecotype to carry 72 chromosomes, so that they're going to have similar amount number of chromosomes as the upland ecotype. That will allow us to cross these two lines together and then generate hybrid vigor, a new plant species for biomass production. So what we did is, our objective is three objectives. Try to generate new lowland switch grass line that have more chromosomes that will be allow us to cross to upland switch grass. We also want to identify microRNA, using next generation sequencing method to identify gene that can control biomass accumulation. And I also want to try to validate this microRNA in plant breeding or genetic engineer. So, so the key approach is using chemical to induce chromosome doubling to see making the lowland switch grass cultivar that has 72 chromosomes. So what we did here is we start from a dry seed, the mature seed of switch grass lowland cultivar called Alamo, and we use this seed to generate a lot of callus. Tissue culture callus basically means you use the seed, let them germinate on the medium, but don't let them produce a plant. So this callus contains millions of cells actually. So every individual cell has a potential to produce a new plant. So with this callus, and we treat it with a chemical